All right, everyone. Welcome to the video for section 3.2. Now that we have this idea of a derivative, which gives us the slope of the tangent line at a particular point on in a function, we're going to expand some more on that and also talk about the idea of differentiability. Okay, and in case you're wondering about this meme here and why it's funny, the guy in the picture is Newton, who is one of the people who invented calculus. And by the way, yes, that's Isaac Newton, who is also super famous for a lot of physics concepts. Okay, so reminding ourselves what we learned in section 3.1. We had these two formulas that are they're the same thing, but think about them a little bit differently. For helping us find the slope of the tangent line and or the derivative. So the first one up there, the m sub tan equals limit as h goes to 0 of f of a plus h minus f of a over h. That's our formula for finding the slope of a tangent line at a point A on a function f of x. And then down here, this notation with f prime of a, remember that apostrophe we read as prime, that represents the derivative at that point. And again, the derivative is just a fancy way of saying the slope of the tangent line. And we're going to generalize the idea of the derivative a little bit more in this section. Okay, so again, this is the idea of finding the slope of the tangent line or finding the derivative at a particular point. But we're going to expand on this a little bit and talk about the derivative of a function more in generality. So rather than every time we want to know the slope of a tangent line at a different point on a function, rather than having to do that whole limit thing separately for each point, we can actually just do it for the function and then use that to find the slope of the tangent line at any specific point. So this definition here is telling us the derivative of a function f, which we denote by that notation f prime of x, is given by f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h if this limit exists. And notice this is different from what was on the previous slides because now we have an x here instead of a's, so we're generalizing. So this x could be any value rather than some specific value. All right, so let's look at an example of this. So the function we were working with in section 3.1, f of x equals 4x minus 3x squared. Let's go ahead and use that limit definition of the derivative to find the derivative of this function. So we will have that f prime of x, again, that represents the derivative, is given by the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? And again, we're just using a general x here, so not any specific value. So we plug those things into the function. So we'll have limit as h goes to 0. Well, f of x plus h means take x plus h and plug it in for x everywhere in the function up there. So we would now have 4 times x plus h minus 3 times x plus h squared minus, well, in that second one, we're just doing f of x, and f of x is just our function, right? So we would do minus 4x minus 3x squared all over h. Okay? So lots of stuff going on. X's and H's and things squared and not squared and just a lot of different things to deal with here. Okay, so what we are going to do now is simplify this. So as you can imagine there on the top, we can distribute the 4 through here. We can square this term and then multiply in the 3. And then here we have this minus sign that has to get distributed into everything inside of here. And so if we do that, I'm going to erase here just to save time and space. And I'll show what we get after we do that. Okay, so what we would end up with there on the top is we would have negative 3x squared plus 4x minus 6xh plus 4h minus 3h squared. And then we'll also have a minus 4x and a plus 3x squared all over h. And again, you could go back and check all the work on that. I'm not going to show all the details right now. And we can go through and cancel some things out. So notice we have a negative 3x squared here on the left, and we also have a 3x squared here, so those will cancel. We have a plus 4x and a minus 4x, those will cancel. And we're left with that negative 6xh plus 4h minus 3h squared. So we can erase everything else up here. They're gone now. And then notice on the top there, we have the negative 6xh plus 4h minus 3h squared. Each of those terms contain an h, right? So we can factor an h out of there. I'm going to write this back over by the limit. So we'd have h times negative 6x plus 4 minus 3h all over h. Erase this other stuff. Okay, oops, did not mean to do that. Okay, and then as we saw in section 3.1, the h's can cancel. So then we just have the limit as h goes to 0 of negative 6x plus 4 minus 3h. And just as we saw in the problems we did before, in this case, h equals 0 is now in the domain of this function, so we can just plug it in for h there to find our limit. And we do that, we end up with negative 6x plus 4. And that would be our derivative, our f prime. Okay. So when we go to write the answer for this, what this will look like is one of the following. Is we would now have that f prime of x, remember that represents our derivative, is equal to negative 6x plus 4. Okay? And then we can use that now to find the slope of the tangent line or find the value of the derivative at any particular point. So thinking about one we did in section 3.1, you remember that we found f prime of 2 for this function. And so if we plug in 2 into the derivative, we'll have negative 6 times 2 plus 4, which gives us negative 12 plus 4, which gives us negative 8. And if you check back in your notes from section 3.1, I think you will see the slope of the tangent line and or the value of the derivative at x equals 2 for this function, we did get negative 8 before. Isn't that sweet? Yeah, I thought you would think that. Okay, so this next problem is one that you guys will do in your classwork. So you have to find the derivative g prime of t of this function g of t, which is given as 10 over t, using that limit definition of the derivative. And once you have that, then you will also need to find each of these, g prime of 1 and g prime of negative 2. Basically just taking each of those values and plugging them in to your derivative. Okay, let's talk about some new vocabulary now that we have this idea of the derivative. So we say a function is differentiable at a particular point A if the value of the derivative exists at that point. So if we can take that point, plug it in the derivative, and get something out. And if we're given that a function is differentiable on an open interval, it is differentiable at every number in that interval. Okay, but the part I want you to focus on here is this term differentiable, meaning that the derivative exists at a particular point. Which may beg a question for you, which is, does the derivative always exist? Would there be an example where it didn't? Well, I'm glad you asked. So let's take an a look at some examples of that. So it is true that a function can be not differentiable at a particular point, or the derivative doesn't exist at particular points. And there are three main criteria we'll look for when we're trying to decide this. So the first one is if the function is not continuous at a point. So we talked in section 2.4 about continuity. If we find a function is discontinuous at a particular point, then it is not differentiable at that point. So looking at this example I have down here, at the point x equals 3, right here, we see that the function is discontinuous, so it is not differentiable there. Now, it can be differentiable at other points on the function, like it could be differentiable at 1 or 2 or 0.5 or negative 0.1, all those sorts of things. It's just at 3 that the value of the derivative will not exist. All right, another point when the derivative does not exist is if there's a sharp point in the graph of the function. Okay, so you see, for example, this one on the left here, we see this, not that, we see this sharp point here. So that's a place where it's not differentiable. And then on this absolute value function, you notice down here, we have that corner piece. That's another place where the function is not differentiable. And can you imagine why the function may not be differentiable at points like that? Well, remember that the value of the derivative has to do with, not only has to do with limits, but it also has to do with the slope of the tangent line, right? And if you think at that corner point on the left there, what would the tangent line look like there? Well, coming from the left, it looks like the tangent line might be something that's going like this direction, sloping up from left to right. Coming from the right, it looks like it might be sloping the other way. So there we see that kind of limits on each side as they relate to tangent lines are not the same. So that would be one example of that. And then I was going to say something else about that. What was it? I'm not sure. I think that's mostly what it was, is that the slope of the tangent line on both sides coming from each direction is kind of not the same. We see a similar thing with this one here on the left. If we're coming from the left-hand side, notice we'd have a tangent line that kind of does this, sloping down from left to right. If we're coming from the right-hand side, it seems to do that. And so it's different from each side. So that's not going to work with us, for us. So that's one of the reasons that the function is not differentiable there. Okay. And then the last one is if we have a vertical tangent line or a vertical inflection point. That would be an example of where it's not differentiable. So looking at this function g of x here, notice at this point where they have the vertical tangent line, okay, that's a tangent line that touches at just one point, but it's a going straight up and down. So it's an example of why it's not differentiable. And if you're wondering about why that is, remember again, the derivative relates to the slope of a tangent line. And what is the slope of a vertical line? Y'all remember? You're right, it's undefined. Okay, which means this is an example of where the derivative, if it's representing the slope of the tangent line, would have to be, the value of the derivative would have to be undefined at that point, which then makes it not differentiable because the value of the derivative doesn't exist there. Undefined is the same as kind of like doesn't exist. All right. Cool. So let's look at an example of identifying places where a function is not differentiable. So remember, we have those three criteria. It's either not continuous at that point, there's a sharp point at the point, or there is a vertical tangent line. So if we look at this, So we see some areas or some points where the function will not be differentiable. Well, I think that one that I see is at x equals -3. Why is that? Well, notice, is the function continuous there? Answer is no, right? We see the limit's the same from each side, but the function value is not the same as the limit, so that's discontinuous. It also looks like it's discontinuous at x equals 1 for the same reason, right? The function is discontinuous there. There's a jump discontinuity. What else do we see? I think I will also say at x equals -2. Why would that be? Well, notice that's where we have a corner or a sharp point in the graph, right? So that short point there is going to make it so that it's not differentiable. Remember, that means kind of the slopes of the tangent lines from each side would be different, so that won't work. And then there's one more. Do y'all see where this one is? Oh, right. There it is. It's at x equals 2, right? Because notice, if we're going to draw a tangent line right there, it would have to be a vertical tangent line, which is not allowed. So that would be another place where it is discontinuous. So we see that our function here is discontinuous at the values x equals -3, x equals 1, x equals -2, and x equals +2. Great. That's all I have for right now. Thank you guys for watching.